Hi, my name is Richa Thakur, and in this presentation I'll be walking you through the design and implementation of an application-specific processor for cryptographic block cipher algorithm. Let's now look at the problem statement. The problem statement was to design, simulate and test for an application-specific processor that works not only for IDEA but for other block ciphers as well with a given set of instructions. Though in this project the target encryption algorithm I'll be using is IDEA. So what is a block cipher? A block cipher is an encryption method that works on blocks of data rather than bits. As we can see in the figure describing the basic scheme of a block cipher, it takes a block of input along with a block of key and using the encryption algorithm to give the encrypted block of output. However, the block size that may differ and depend on the different encryption algorithms. Now let's understand the basics of IDEA algorithm. In this project, the target algorithm which we were supposed to implement was IDEA. IDEA stands for International Data Encryption Algorithm, introduced by Lion Massey as proposed encryption standard in 1991 and later improved it and renamed as IDEA in 1992. IDEA works on three key operations. First, modulo addition, second, modulo multiplication, third is bitwise XOR. To encrypt the 64-bit plain text input along with 128-bit key into a 64-bit ciphertext by iterating 8 times followed by a final output transformation round as shown in the figure. Now let's have a look at the choices I made. The main challenge in this project was to have an architecture which was optimized for high throughput and low latency with the given set of instructions. The table here shows the options I had for designing my processors and their basic comparisons based on different factors. So looking at the table, the pipeline is the winner in terms of throughput and latency. Thus, I chose to go with the 5-stage pipeline architecture for my processor. Also, to optimize the throughput and latency, I decided to have a dedicated hardware for complex modulo operations used in the IDEA algorithm. I read a lot of IEEE papers, journals, and found that modulo multiplication is a critical element in IDEA algorithm-based processors' performance, and optimizing them is the most important task. However, no dedicated hazard unit is implemented as such. In case of any hazard, the processor stalls, which ultimately hurts my overall CPI. So future modification in this processor could be done to have a dedicated hazard unit to improve the performance. Ahead with my architecture's abstract picture. The figure shows my abstract project architecture which I have implemented in Java. The project implementation required the direct upload of memory image in the form of hex file. However, I have an additional feature in my architecture which is a parser. The parser takes the assembly code and generates its hex code which is stored in the memory and is given to the processor using parsing logic in the form of lookup tables and hash map in Java. Also, my architecture supports the direct upload of memory image, that is hex file as well. The memory used is CMOS SRAM with a capacity of 16K, and a single memory is used for storing keys, input data, program and the output generated from the processor. The memory is byte addressable and each line has 32 bits. Thus, the PC needs to be incremented by 4 every time the next instruction needs to be fetched, since all the instructions are encoded in 32 bits. Keys are pre-calculated and stored in the memory. The processor takes the input and compute the output with a pre-calculated key stored in the memory. The 1024-bit input and 128-bit keys are configured in the config file and it gets loaded into the memory. The processor is a black box which will be detailed further in upcoming slides. My processor has 5 main steps, that's the pipelining stages: fetch, decode, execute, mem and write back, and has an interrupt mechanism which, if gets activated, stops the current execution. The instruction set encoding. There are 32-bit general purpose registers used. All instructions are encoded in 32-bit format, that is fixed length format, as that will be easy to implement in pipelining. Variable size instructions improve the architectural matrix but makes the instruction decoding more expensive and hence is not a good predictor of performance. The key was to support as many addressing mode as possible. Since only 15 instructions were provided, using many addressing mode could be a smart option to use the same instruction in different ways. For example, the same load, which is a memory access instruction, can work as move instruction in register addressing mode. There are 3 broad classes of instructions. Let's understand the format of ALU operation. The first 2 bits indicate the addressing mode. The next 3 bits are for opcode. Bits 5 to 7 for function bits. Bits 8 to 12 are for the first operand. Bits 13 to 26 are padded 0, which can be used in future to increase the operand or for any other improvement. Bits 27 to 31 is the second operand. Now, memory access operations, bits 0 to 1 to determine the addressing mode, 2 to 4 for opcode, 5 to 7 for function, 8 to 12 for the first operand, 13 to 26 for the 14-bit offset, and 27 to 31 for the second operand. In jump and branch, the 0 1 addressing tells the addressing mode, 2 to 4 tells the opcode, 5 to 7 function bits, 8 to 12 for the first operand, and 13 to 31 are for the memory address, which needs to be given in the form of line number in the assembly language, and the processor is capable enough to determine the address through the line number of the code. There are 3 addressing modes supported and are decoded as from the LSB bits. If 00, it's register addressing mode, 01 immediate, and 10 is for displacement addressing mode. Let's understand the architecture and data path through an example. So this is my 5-stage pipeline architecture with the 5 stages as shown: fetch, decode, execute, memory access, and write back. Let's say there is an instruction at memory location 12, which is add R1 R2, and another instruction at memory location 16, which is mod mul R3 R4. The current value of PC is 12, 00C in hex. This value of PC will be transferred to MAR and PC will be incremented by 4. The instruction will be fetched from memory and will be stored in MBR in binary format as shown. Then this instruction will move to decode stage and the bits 0 to 7 will be given to the control unit to generate the required signal to be given to the execution unit. Once the first instruction moves to decode stage, the next instruction gets fetched from memory location 16 and the value of PC will be transferred to MAR and PC will be incremented by 4 again. In the decode stage of instruction 1, the control unit gets the input 00000000, which indicates register addressing mode, and addition operation needs to be performed. The bits 8 to 12 of MBR will be given to the register file R1 and bits 27 to 31 to the register file R2 and bits 13 to 31 will be given to the SE unit, that is sign extend unit. The 32-bit data from data 1 and data 2 will be given to the execution unit. In the execution stage of first instruction, the second instruction will be decoded in the same way. The output from the decode stage will be given as the input to the execution unit, which goes through the muxes, depending on the signal from control unit, as to select which data will be forwarded to the ALU. After the data is forwarded to ALU, the ALU operation signal from control unit will be given to the ALU and desired operation will be performed on the operands. Then it enters the memory access stage and the next instruction enters the execution stage. In case of load store instruction in displacement and immediate addressing mode, the memory will be accessed, otherwise the instruction will go to write back stage, where the result from ALU will be written back to the reg file destination register R1 and the next instruction will move to the memory stage and subsequently to the write back stage. So this is how my 5-stage pipeline is working. Look at my architecture's performance evaluation and calculation. Starting with the testing of 1024-bit input is shown along with the 128-bit key. To verify the results, I double check my results with this Java applet link shown here. The throughput I got is 72.41 megabits per second for the 1024-bit of input. The latency, that is the time when the first 64-bit of ciphertext was generated, is calculated and it comes out to be 0.9 microsecond. The CPI of my architecture comes out to be 1.18. Total number of clock cycles to compute 1024-bit input is 5336 clock cycles generated from the global clock. The clock cycle time for 5-stage pipeline processor is the maximum time taken by any of the 5 stages, and that comes out to be 2.65 nanosecond, that is from the execution unit. Finally, the total execution time is 14.14 microseconds. All the calculations are shown in a calculation matrix document being provided along with the code. This is my assembly code for the IDEA algorithm, and there are total 61 instructions, and the plot shows the frequency of instructions being used, wherein the load dominates and are responsible for 45% of the instruction executed, mod ALU for 20%, ALU for 17%, store and branch for 7%, and jump for just 4%. Now reviewing some of the literature of hardware implementation of IDEA algorithm. This is the first literature I reviewed, which was published on Microsystems and Microprocessor Journal in 2005. This VLSI implementation was done by M. Tandoori, SMU, ArgIDE at 100 MHz clock frequency that gave a throughput of 700 megabits per second using 8 pipeline stages and parallel multipliers for modulo operation. This is the second paper I reviewed and is the state-of-art implementation of IDEA hardware done by Granado, Miguel, and Joan in 2009 and was published in Microelectronics Journal. In this design, 2 cryptographic algorithms were implemented on Xilinx Virtex 6000 FPGA using Handle C, VHDL, and JBits. 182 stage of pipeline and constant coefficient adders and multipliers were used to achieve high performance. This design gave a throughput of 27.948 GB per second for IDEA, which is the highest till date. Now let's have a look at the comparison table for the previous IDEA hardware implementation published in Information Security Journal 2011 done by Saurav Mukherjee and B. Sahu. All the designs with their operating frequency and throughputs are compared, where Grenado achieved the highest throughput among all the implementation done till. Comparing the state-of-the-art implementation with my architecture, the transistor count and throughput both are tabulated, and the cost in terms of throughput upon number of transistors comes out to be 180 for Grenado and 36.61 for my processor. With all the constraints, my processor has achieved an appreciable throughput rate and has lesser cost than the state-of-the-art implementation. Moving ahead with the special features implemented in the architecture. In my design, there are two special features. One is the inclusion of parser to generate the hex file from the assembly code, and the second is the modulo operation, which is not limited to 2 power 16 and 2 power 16 plus 1. There are two registers, R11, R12, which has the value of the modulus with which the modulo operation needs to be performed on the input. This slide I mentioned all my assumptions and justifications supported by the documents being referenced. The key assumptions were modulo multiplication is the critical path and takes a clock cycle time of 2.65 nanosecond. All other operation takes fewer clock cycle compared to modular operations. Memory used is CMOS SRAM whose capacity is equal to L1 cache and has faster access time. Finally, concluding my presentation, I'll point the key features of my architecture, focusing on the strengths and the weaknesses. 5-stage pipeline architecture was implemented. The processor can work for any other block cipher algorithm using given set of instructions. Inclusion of parser helps to simulate the processor system using assembly code as well. The user input and key are easily configurable in the config file. Complex modulo operations are implemented using special hardware to optimize throughput and latency. However, the major drawback is the absence of a dedicated hazard unit, and a detailed trace file has been provided showing the complete tracing information about the processor steps and output. Now here are the references I used during the making of my processor architecture, and thank you all. I'd like to thank my professor for all his help and support. For any further feedback or query, write